Hi, my name is Matthieu Darcy, and I'm here to present the Kernel Flows algorithm and its application to regression problems. This presentation is based on research I've done at Imperial College London under the supervision of Boumediene Hamzi for my master's thesis. The presentation will be as follows. I'll first quickly present the basic elements of kernel regression. Then I'll present the Kernel Flows algorithm, both its parametric and non-parametric versions, and numerical experiments on regression datasets. The Kernel Flows algorithm is based on a 2019 paper by Houman Ouadi in Jinra Yu titled Kernel Flows from Learning Kernels from Data into the Abyss. If you're interested in recent theoretical results, I suggest you see the presentation by Yifan Chen at this link below. If you're interested in the code used for the numerical experiments of kernel flows, you can find it at this link. So what is the regression problem? Well, given a set of training data, we wish to predict a dependent value y from a new data point x. Our basic assumption is that y is generated by some function of x and some parameters theta and some noise, generally some Gaussian noise, which is independent for each data point x. In the regression model, we can first transform the data using basis functions phi. And these basis functions do not have to be linear. The kernel regression model is based on a kernel function, which allows to solve the regression problem without explicitly computing these transformations phi. And this has the advantage of being able to use very high dimensional transformations or even infinite dimensional transformations because we never explicitly compute the transformation itself. So the kernel regression is based around the notion of a kernel function. And a kernel function is a function of two arguments of x, and it's a symmetric function, and it must form a positive definite matrix. Each kernel function will define a Hilbert space called the reproducing kernel Hilbert space, or RKHS for short. The main result in kernel regression, which allows us to solve the regression problem, is called the representer theorem, and it says that the minimizer in the RKHS, in the Hilbert space defined by the kernel function, the minimizer in the space of a loss function takes the form this. That is, if you fix the first argument of your kernel function, it becomes a function of one variable. And the representer theorem says that a linear combination with coefficients of functions of this form, where xi is the training data, this function, a function of this form, will minimize a loss function. And it will, the representer theorem applies to a very large class of loss functions. However, in the linear regression setting, we're interested in the mean squared error loss function, which basically is the difference between the predicted value and the true value, the predicted value and the true value for each training data point squared. There's some added regularization term which prevents the model from overfitting and puts a bound on the size of the coefficients. In the case where the minimizer is this mean squared error function, the coefficients in the minimizer are given by this vector. The expression k of xs is a n by n matrix with ij entries given by this, where the xi and xj are training data points. So this is a vector. This can be summarized as follows. A new prediction of a new data point is given by the dot product between the coefficients, the vector of coefficients, c, and this vector here with entries given by this. And again, xi are training data points. The regression model requires the use of a kernel, and popular kernels include the Gaussian kernel, the polynomial kernel, and the rational quadratic kernel. Notably, the Gaussian and rational quadratic kernels are so-called universal kernels, which means they can approximate to an arbitrary value any continuous function in the supremum norm. So as a quick recap, kernel regression allows us to apply linear regression to high, even infinite dimensional feature maps. The regression function is a member of the Hilbert space defined by the kernel, and the kernel regression requires a kernel function and associated parameters. So the central problem in kernel regression is that parameters greatly affect performance. Moreover, there is no obvious answer to what is the best parameter. And this has the problem of how do we find the best parameters, and in general we're led to doing a grid search, which is testing a large amount of parameters and seeing which one gives us the best result. An alternative is given by Houman Owadi and Jane Yu, and what they do is they provide a numerical scheme to answer this problem, and the numerical scheme is called kernel flows, and it was first presented in the following paper. So the intuition behind kernel flows is the idea that a good kernel is one where removing half the points leads to a similar performance as using all the training points. And this is quite intuitive. If you think of the central problem in machine learning, the central problem is generalization. How do we go from a training data set to extrapolating into new data points? This is essentially going in the other direction. It's saying generalization is achieved when you can remove some of the data, the training data, without significant loss in performance. The problem with this formulation is it requires the notion of defining the notion of similar performance. In machine learning language, this means defining a loss function associated with the problem. In the original paper, they define the loss function and call it rho. And it's defined as this. If you consider u of b as being the function, the regression function, which sees all the training points, and if you call u of s the function which sees only half the training points, then the loss function is defined as the norm squared of the difference between these two functions. And then we normalize by some value, which is the norm squared of the regression function, which has access to all the training data points. And in this case, the norm used is the RKHS norm, that is the norm of the Hilbert space associated with the chosen kernel. So in this case, similar performance is defined as proximity in the reproducing kernel Hilbert space. They also derive an explicit formula for this loss function, which allows its computation and the computation of a gradient. So if you call xs the x points associated with half the training points, and you call xb the x points associated with all the training points, if you call ys the predicted values, well, the true predicted values of half the training points, and yb to be all of the training points, then the rho function takes this form. So the kernel flows parametric version takes this form. You first select a batch of points from the original training data set, and this batch can contain all the training data points, or it can contain a subset of these training data points. And this selection is done uniformly at random without replacement. You then select a sample from the batch which has half the data points. You then compute the gradient with respect to the parameters of the rho function. You then update the parameters theta in the direction of gradient descent. So kernel flows is a gradient-based algorithm, and you repeat this procedure as long as needed or until convergence to some arbitrary value. And each time you select a new batch, a new sample. So a few considerations is, first, we don't have to actually use half the batch for the sample. In fact, we can use a sample size which is p times the batch size, and p is a free parameter. You're setting p equals to 0.5, you get back the original proposal. The computation of the gradient with respect to parameters can be done using an explicit formula, which was derived in the original paper, or using a numerical differentiation package such as AutoGrad or JAX. The update rule, like in any gradient-based algorithm, can be changed, and in particular I consider the Nesterov momentum update rule. So the algorithm is based around the rho function. So what does rho look like? Well, the first observation is that rho is non-convex. This is rho plotted as a function of the parameter sigma in the Gaussian kernel. And you can see that obviously it's not convex. That means that any gradient descent based method does not necessarily converge to the true minimum. It can converge to a local minimum. And this will depend on the initialized value of the algorithm. However, there are a few ways to get around this, a few solutions. The first is to use a different gradient update rule. So this case is the Nesterov momentum update rule, and the Nesterov momentum keeps track of past computed gradients in the ZK term, and this is referred to as the momentum. This has the effect that if you get in a local minima, even in a normal in the normal stochastic gradient update rule, it's impossible to get outside this local minimum because the gradient will be 0 at that local minimum. But in the case of a Nesterov momentum update rule, the past gradients can in some cases get you outside of this local minimum because it has remembered all the past gradients. The second solution is to use a smaller size batch. So instead of using all the training data, you can use 100 or 200 data points. And the reason why this can be a solution to this problem is because smaller batches have increased variance, which means that you have a higher chance of finding a batch sample combination which does not have a local minima at the average local minima. So you can find a batch sample combination which will push you outside the average local minima. And finally, it's to simply use different initialization values and just finding the one that gives you the best results. The second consideration regarding rho is that rho is affected by noise in the data. So consider a data set which is generated by a sine function, and the associated rho as a function of the parameters. This is a Gaussian kernel, and the parameter is sigma. And as you increase the noise, the first one has no noise, the second one has Gaussian noise with variance 0.01, the rho function changes, and this has variance 0.1. And you'll notice that not only does the minima change, the shape of the function changes as well. It becomes flatter. There's less difference between different parameter values. And the reason why this is the case is because greater noise means that it's harder for different parameters to perform well, which means that every parameter essentially performs similarly. They're all pretty bad at predicting the data. And hence, increased noise will mean that rho becomes more equal across parameters. Finally, rho also is affected by the proportion parameter p. This is an example. In the first case, we have the sample size is 1/4 of the batch. Second, it's 1/2 of the batch. And finally, 3/4 of the batch. And you can see that if the minima is slightly different in each case, but still similar. But also the amount by which rho varies can also change, which means that the gradient, the absolute value of the gradient, is in this case more important when the sample size is small. This leads to the conclusion that there are some advantages to using a smaller value of p. The first one is that smaller values of p encourage greater generalization. If you think of using half the batch as sample as encouraging the kernel to generalize, using a smaller sample will encourage greater generalization. Second thing is that in some cases rho will vary more with smaller proportions, and hence the absolute value of the gradient, in other words how much we update the parameters at each iteration, will increase. And this can lead to improved performance by the following consequences. Is that first, the chosen parameters will be chosen to encourage greater generalization. The second thing is that it can also increase the rate of convergence to the chosen parameters because the update is larger in each case. However, this is not systematically true. In some cases, using p too small can lead to adverse effects such as lower generalization, because when you have a sample size which is too small, every kernel becomes equally bad at predicting the sample, and hence you have again equality between parameters, which is undesirable. So this leads to the following suggestion, is that we should modify or use different values of p. The first proposition is to use a small proportion and linearly increase this proportion as trading continues. The reason why this may be advantageous is because in the beginning, your kernel is bad. It doesn't perform well, and hence using a small proportion will quickly push it in the direction of a good performing kernel. And as you train, your kernel becomes better and better, and hence you want to go back to the original proposed 0.5, and hence you increase the proportion to get back to the original proposed value. The second suggestion is to simply set the proportion to some small value p less than 0.5. You can use 10%, 20%, or 30% for example. The third suggestion is to use a value which changes across training and which takes this value. The intuition behind this is that the expected value of rho gives you an idea of how well your kernel is performing. And what you expect is that at the beginning, your kernel performs badly, and hence this value, the expected value of rho, will be large, and therefore p will be small, and again this will push it quickly towards better values of theta, of the chosen parameters theta. And as you train it, the expected value of rho will diminish because your kernel will become better and better, and hence p will get closer and closer to the original proposed 0.5 value proposed in the original paper. Now, obviously, we don't have access to this value, and hence, as a proxy, we use the running average of the previously computed rho values, and then we average that over k previous values, and we use this as a proxy for this, the expected value of rho. Now, what are the numerical results? Well, the first thing is that, we tested kernel flows on the Boston housing dataset, the wine quality dataset, and the diabetes dataset, and all of these are available online. Kernel flows in general did improve the performance of the base kernel. So this is a typical results table, and you can see that in each case, the mean squared error and the mean absolute error went down. In general, also, using smaller batch size can improve the performance. So this is an example on the wine dataset, both the red wine and white wine dataset. In each case, we used a batch of 500 and then a batch of 100. And in each case, the mean squared error went down by about 7 to 8%. Also, using a smaller proportion of p, or an adaptive value of p that changes throughout training, does also, in some cases, improve performance. So this is an example with the rational quadratic kernel and the red wine dataset. And in this case, we had the MSC went down and the MAE went down. In the case where you used a linear combination of Gaussian kernels as our kernel on the red wine dataset, using a small value of p at only 10% also meant that the mean absolute error went down. However, all of these results will depend both on the data and the method. That is, on the dataset that you're training on, and on the chosen kernel, the parameters chosen, the initialization, and the update rule for your parameters. So these aren't absolute truths, and you have to test it out. However, on a slightly more pessimistic note, sometimes the performance was not improved, and in some cases it worsened. This relates to the problem of non-convexity of the rho function and its relative flatness. This is a case where we had a 2-parameter kernel, and you can see that both parameters oscillate without settling on a specific value, and the rho function also oscillated a lot without diminishing. And this is a problem that we initialize our kernel in a region which is close to a local minima, or where the base kernel is already performing quite well. In this case, kernel flows cannot improve the base kernel. Okay, so moving on to the non-parametric version. What is the non-parametric version? Well, the basic idea is that instead of modifying the parameters, we should modify the points. So the algorithm is as follows. We select a base kernel k. Like the parametric version, we select a batch and sample in exactly the same way. And then for every element in this batch, we compute the gradient with respect to the rho function for this particular point. For each point not in the batch, we predict the g value based on interpolation by the base kernel k. So g is the vector of these gradients for every data point, and this is the prediction given by the kernel K. And you then adjust the point, you perturb them by the value chosen, the G value. And then you repeat this a certain number of times as you find fit. This leads to learning kernels of this form. K of n is the base kernel applied to the fn function of xi and the fn function of xj, where the fn is every single time is defined as a small perturbation on the original point. It's important to note that the algorithm depends on the base kernel K in two ways. First of all, it will determine the gradient computed for the elements in the batch. Second of all, it will determine the perturbations by interpolation of the gradients for all the elements not in the batch. So it will depend on, the perturbations will depend on these two things in two different ways for the base kernel. An important thing to note is that this version of the algorithm is very vulnerable to small changes in the data or the parameters. So this is an example where we use the Gaussian kernel with sigma is equal to 2 on the Swiss roll dataset, which is two spirals with values 1 and -1. And you can see that after 10,000 iterations, the algorithm linearly separates the data, a very desirable result. However, this is what happens when we use sigma equals to 4 instead of 2. In this case, in the case where you have low regularization, the data becomes all jumbled and the predictions aren't good. But in the case where you use a higher regularization term, you actually go back to the linear separation case, which is again very desirable. However, if you increase again sigma to 5, for instance, this behavior disappears. This linear separation behavior disappears, no matter how much you regularize your base kernel. And this is a general problem in the method, is that it will depend on the perturbations, on how much you update the points at every time, the kernel, the form of the kernel, and also the parameters. Again, we tested the algorithm on the Boston housing dataset, the wine quality dataset, and the diabetes dataset. And every time the non-parametric version did minimize rho, but it did not improve the mean squared error. So you can see in this case, this is one example, but there are others, is in the original kernel and the prediction after transformation by the non-parametric version, you can see that the MSE goes up by 18% and the MAE goes up by 7.3%, which is undesirable. So there are several options that explain this behavior. The first option might be that our parameters are non-optimal, and by this I mean the parameters of our original kernel, the size of the perturbations. Every time we perturb the points, the perturbation might be too big or too small. It might be the number of iterations. It might be how much we regularized our kernel, and this speaks to the fragility of this method. And finally, the second option is that our choice of base kernel might be wrong. And by choice of base kernel, I don't just mean the parameters associated with the base kernel, but the general form of the base kernel. So in the previous slide, I showed you kernel flows with a Gaussian kernel, but it might be that we need to apply this to other kernels which might perform better with this method. So that was my presentation. I hope you found it interesting. Again, if you're interested in the code I used for these numerical experiments, you can find it here. If you're interested in further reading, you can find the original paper and recent theoretical results at these links. If you're interested to the applications to dynamical systems of the kernel flows algorithm, you can find them at this link. And if you're interested in applications to neural networks, you can find it at this address. Thank you very much for watching.